So first of all, I'd like to thank everybody for joining us this week in our first virtual distinguished lecture series of the semester. And I'd like to thank everybody who sent me and gave me suggestions for speakers for this semester. I basically took the list, had about 30 suggestions or so, and basically took that list and started to try to make it sort of as diverse as possible in terms of the variety of topics that are discussed and so on. And so basically everybody that I invited said yes to this series. And so I think that it was like we got like our top 12 speakers basically for this semester. So I look forward to this as being a really interesting set of talks. So today, of course, it's my great pleasure to announce our first speaker, who's Dr. Zach Ross, who comes to us from Caltech. Zach, he completed his Bachelor of Science in Physics from UC Davis in 2009. And then he went on and did a Master of Science in Civil Engineering at California Polytechnic State University in San Luis Obispo, which he had completed in 2011. After that, he did his PhD in Geophysics, which he graduated in 2016 from USC. And then my understanding is he's been a postdoc at Caltech from 2016 to 2019. And now he is assistant professor at Caltech. And then I'd also just like to note that in 2019, he also won the Katie Aki Early Career Award from AGU. And today, he's going to tell us then about 3D fault architecture controls and the dynamism of earthquake swarms. So, thank you, Zach.
Yeah, so thanks for having me back here. This is always a good crowd. So today I am going to talk to you about a really spectacular earthquake sequence that we've been looking at for about 4 or 5 years now. So I'll just kind of jump right in. So earthquakes are, I think it's very well recognized that they are not just individual events, but they are members of sequences. And so when we think of earthquake sequences, the standard one is what we would call probably a main shock aftershock sequence, which looks something like this. So this is magnitude versus time here for a sequence that we had in 2014, La Habra, California. And so this is punctuated by, there's a magnitude 5 main shock, followed by a bunch of aftershocks for about 30 days, and it decays basically back to the background level, and so forth. And so in a sequence like this, you might have the situation where there's a few foreshocks that occur, and then the largest event will happen. That becomes the main shock because of its magnitude. And you are followed with aftershocks, which decay with time like 1/t, and that's the Amori law. And so I think, if you look at something like this sequence, today I think it's fair to say that we understand this type of pattern fairly well. It's viewed today as most likely being driven by some kind of earthquake stress transfer mechanism, and most likely due to static related triggering. But there's another type of earthquake sequence that we would call an earthquake swarm, and this is quite a different type of sequence, fundamentally different. And so here's an example of a swarm that happened in Eastern Germany back, I think 2001. So here again, magnitude versus time, except this is now 120 days. And you can see lots of bursts of activity. It's very complicated. It's not simply just decaying with time. So earthquake swarms are associated with areas that often have some kind of elevated heat flow or rifting, hydrothermalism, magmatism, etc. Although it's not always the case. There are some examples that are not. Swarms are quite special because each one has some kind of unique evolutionary pattern in space and time. And the behavior during a sequence is highly non-stationary. And so compared with this type of main shock aftershock sequence where the rate just decays like 1/time, here this is something much more complicated than that. And so swarms have a number of distinguishing characteristics that I think are important to note. One of them is that often we see that the largest event occurs quite long after the sequence will initiate. So here, for example, the magnitude The largest event in the sequence is, 70 something days into the sequence. It's often the case that there's not just one standout magnitude, it's that there's many events with a similarly large magnitude. And swarms often can last for days to months. They sometimes surge on very rapidly and shut off just as rapidly. And they commonly exhibit some kind of spatial migration. And so that means that if you look at the epicenters or the hypocenters, that they're moving with time. And so when you look at all of these different characteristics together, today we believe that swarms are driven by some kind of aseismic process, primarily, as opposed to standard main shock sequences being driven by earthquake stress transfer. And the leading causes of these aseismic processes are today believed to be fluid migration in the earth and aseismic slip. And so we can take these, we can compare them side by side. And so again, I think this type of sequence on the right-hand side, we understand fairly well. We don't understand necessarily when this sequence might initiate or all the nuances of it, but the patterns, at least in terms of a physical basis, we have a pretty good grip on, I think, at this point. However, I can't look at this and tell you what all of these different bursts of activity mean and why it's surging on and off and why it shuts off here after 120 days just so suddenly. And so what's really incredible about swarms is all of this dynamic behavior that we see, which we really don't understand very well. And I think it's reasonable to ask how much of this behavior reflects a lack of knowledge in the structural and permeability architectures of fault zones, because if in particular swarms are driven by fluid behavior, then the permeability structure is going to become quite important. So it's worth, I think, taking a step back and looking at what we really know and believe to be representative of the character of fault zones, the architecture of them structurally, permeability-wise, and so forth. This is kind of a standard cartoon for general fault architecture, where you have a fault core that's containing the principal slip surface, which is highly localized. You're talking about meter scale or so for the core. That might be surrounded by damage zones with lots of distributed cracking that exponentially decays with distance from the core. Eventually decays to some kind of country rock. But often we see stuff that happens where there's damage distributed for kilometers or so. This shows up often in thermography. And within these fault zones, it's really not just a single surface. I think it's important to point out that we know that there are many smaller faults and cracks that are embedded within these systems. So it's really a zone of faulting. And I think this is fairly well recognized. But I will point out that these cartoons like this don't tend to do a good job of emphasizing that aspect of these systems. So that's kind of the structural architecture. In terms of permeability architecture, there's a variety of different ways of thinking about this. One of the kind of prevailing ways today is to think about this in terms of barriers and conduits and the different components of these fault zones acting like that. So for example, if you have a series of faults like this, often people will think about this in terms of how the core and the damage zone together combine to act as either a conduit or a barrier type of system. And so here, for example, this is like a line profile of permeability across a fault. And in this case, it's this fault right here, where when you're within the damage zone, that's basically viewed as some kind of high permeability medium because it's highly fractured. And then once you go across the core, that permeability drops significantly, at least in this framework here. Or if you have multiple faults, it might have some kind of pattern like this. And these authors try to synthesize these observations by saying something about how, how much of the effective fault zone width is taken up by the damage zone. And that can translate into different types of systems where you either can have a localized conduit, localized barrier, or some kind of distributed conduit system and so forth. And that also depends on, at least in their view, how much of the fault core contains low permeability materials. And I think this is a fairly representative view of kind of the general architecture of fault zones today, which is really kind of, it's very one-dimensional in this sense. It's kind of in a profile in a fault normal sense. However, I think it's well recognized that often the permeability of fault zones is can be quite anisotropic. So here you have some kind of schematic of this fault zone here. And then if you look at this model here, where you have all these permeability ellipses, so here, within the damage zone and the core, these are highly elongated, and it's supposed to represent that these are strongly anisotropic materials, and that might relate to the wear products and things like that, kind of fabrics within them. And this is important not just for earthquake science, but also I'll note for hydrologists who do simulations of flow within fault zones. So for example, if you have aquifers that are offset at different depths, well, if you have a fault zone like this that has strongly anisotropic material, that can enable the connection of aquifers at different depths accordingly. So this is important to a number of different disciplines within earth science to understand the permeability architecture of these systems. So, and permeability is, in reality, it's most likely not a static property. It is probably transient. There's a lot of evidence that that fluid flow in the earth can behave highly episodically. And in particular, the structural geologists have looked at mineral deposits, gold, things like that. A lot of these veins have evidence for episodic behavior that might consist of high fluid flux transmission within a fault zone, and kind of characteristic cycles of this type of behavior. And so here, for example, is a model for natural injection-driven seismicity, where you have some kind of reservoir at depth, and pressure builds up in that reservoir and eventually exceeds some critical threshold where the seal of this reservoir breaks and fluid is now injected into a fault, and it starts to drive seismicity as those fluids would diffuse through the fault zone and so forth, until it eventually reaches some kind of conditions that reseal, and the whole thing pauses while you repeat this process and pressure builds back up. So this is kind of a model for injection-driven seismicity, where the fluid is acting as a way of driving this kind of earthquake swarm activity. And so this model, I think, is important, and I'm going to come back to it a bit later, so keep that in mind. Okay, so hopefully that gives you kind of an overview of where a lot of the prevailing thought is on these models for fault architecture. These models are, and I'll call this general fault architecture because I'm not talking about what a single fault looks like. It's kind of a model in a very general sense for many different types of faults. And these models are compiled primarily from geological and hydrological measurements near the surface. I think that's not surprising probably to most people. And occasionally we can augment these models with fault samples from deep drilling projects. So for example, this JFAS project, where they drilled down into the megathrust that produced the Tohoku earthquake in 2011. And so they can take these samples out. They're extremely valuable because you're measuring it right on the fault at depth. But the issue with this is that it's highly sparse. And so we take this one sample or a handful of samples from a handful of sites, and we then try to infer something about what's happening everywhere else using this information. And I think, in a lot of ways, that's the best that we can do. But I think it's important to recognize that what this really still means is that most of the information contained in these general models is still effectively two-dimensional. And so when you think back to these cartoons that I showed you before, these are kind of line profiles in a fault normal sense here. This, again, when talking about the structural architecture, almost all the variability in this cartoon is shown in a lateral sense here. And so I think this is important because this doesn't actually mean that we think that fault zones are really 2D systems. But I think the lack of information that we have as a function of depth leads us to often assume that fault architecture very smoothly with depth, even though for individual faults, when we have really good information, that this really doesn't seem to be the case. And in particular, in the last decade alone, there's been a lot of studies, particularly from seismology, looking really deep, that have found quite good evidence that really it is not smooth variations of fault architecture with depth, that it can change quite drastically. And so here's some examples. So here's one from a paper that, Amir published several years ago. This is in Southern California. It's a tomography study focused on the San Jacinto fault zone. And there are very strong depth-dependent variations in, VPVS and the ratio on fairly short length scales, a few kilometer scale. And this is after you have a model that's very smoothed over. And we know that this is much smoother than the real thing. And so even in this type of model, it's very clear. We should not just assume this is going to be weakly depth dependent. We know from seismicity studies, which are very high resolution, here's the Ridgecrest earthquake sequence from last year, where all these are epicenters of the sequence. And we have lots of different faults at lots of different scales. They don't all cut through the entire seismogenic zone. So here's a profile from the northwest to the southeast. We can see lots of things, everything from tens of kilometer scale to 1 kilometer scale and smaller. These things start and stop all the time. That means that in terms of if you're considering fluid flow patterns and things like that, it's going to be very heterogeneous. It's not just going to be a simply continuum extension with this fault normal type of behavior controlling all of the variability. And so I think it's important to really consider these aspects because, again, if we want to talk about earthquake swarms and the properties of the fault zones that are potentially explaining all of this complexity that we see, we need to really get a better grasp of what this type of fault zone variability really is. And so with that, so the sequence that I'm going to talk to you about today, we call this the Koya sequence. This is really a spectacular sequence in Southern California's history. This is a 4-year-long earthquake swarm that started back in 2016. It has lasted 4 years, and today it basically is tapered off at this point. And so this sequence, you can look here at the number of events. It started off very slowly, and then starting around 2017, it started to accelerate in terms of the rate. It stayed fairly steady with time until about mid to late 2018. And then it had the largest event of the sequence at that point. So 2.5 or so years into the sequence at a magnitude 4.4. And this changed the character of the sequence in a number of different ways, not just the rates here, but it had a very prominent signature. And I'll show you that more very shortly. So this sequence is occurring within this red box here. So this is the Elsinore, San Jacinto, and San Andreas fault zones. So this is kind of in the middle of 2 major fault zones. It's in the peninsular ranges and crystalline rocks. This area is not noted for having swarm-like activity. It has relatively average heat flow. There's no kind of hydrothermal activity that's been documented around here in any extensive way. And so I want to point out that this swarm, the duration and several other attributes about it, I think would make this basically an anomaly by most definitions of earthquake swarms globally, because typically swarms last anywhere from days to weeks, and occasionally they can last months or years, but there's been a handful of cases globally that have lasted for more than several years that have been documented. And so here at 4 years, this is quite unusual. Okay, so this gives you kind of an overview of the area where this occurred. And so we have this standard earthquake catalog that is produced by the Southern California Seismic Network. That does a decent job of giving you a first order characterization of what's happening. But in the last few years, I've been working a lot on developing algorithms for improved earthquake detection and location and phase association, which is basically all a bunch of tools for doing better job of monitoring. And in particular, the advances have come from the adoption of artificial intelligence algorithms to do this. And so when I was here last year, I kind of went into a lot of this stuff in quite a bit of detail. So I'm not going to spend much time going over this, but for those of you that haven't heard this before, basically we are going to use two different algorithms here. One that basically is designed to scan 3-component waveform data that looks just like this. And every time there's an earthquake in the data, the algorithm is designed to basically identify it, log the time that it thinks that the earthquake is occurring at, so the onset time of different types of seismic waves. And this is basically a single station detection algorithm. And so from here, we would apply this to all of the waveform data in our data set. And we can then essentially try to make sense of all this stuff at a very high level. So we really work with networks of sensors. It's not individual sensors. And so here, for example, this is basically a cartoon of what might be happening across the entire network in space and time. So every one of these little circles is supposed to be basically a tentative detection of an earthquake at some latitude and at some time. And so you see here in this cartoon that there's some patterns that have basically a move out of different types of seismic waves. And so these are supposed to indicate basically an earthquake that's propagating through the network. And so we have an algorithm that, again, is using AI to look at all of this stuff here and try to make sense of it. It's basically a decision module that says all of these things here basically can focus back to a single point. That's the hypocenter. And we can then group those together and treat them all as part of the same event. And so I'm not going to go into any more detail about this, but I'm happy to discuss this more later or point you to our papers. And this at this point is, this is beyond tested, and it works quite well. So so we're going to take these algorithms and we are going to use them to batch process all of the continuous waveform data within here. It's 50 kilometers of this little red box. So every blue triangle here is one of our seismic sensors for the last 4 years. So this is a reprocessing of all of that waveform data. And so we run the first algorithm, the single station detection algorithm. We run our decision module, the phase association algorithm. And we then locate all of the events during that 4-year period with a probabilistic hypocenter inversion algorithm, Nonlin lock. And what that leads to is all of these hypocenters that you see over here. And so in total, there are about 23,000 events that we detected with these algorithms. And that's considerably more than what was originally listed in the regional network catalog. And you can see here already that the scale of this is quite compact. So this is just 1 kilometer. So, the whole size of this thing is only several kilometers, at least to the extent that these locations are accurate. And so we can take all of these events, we can then attempt to refine their locations further by using more precise ways of measuring arrival times. So we're going to use a form of waveform cross correlation to measure the relative lag time between different waveforms. And we use an algorithm called GrowClust, which is basically a cluster-based event relocation algorithm to then shift all these around in a much more precise way. And so what that does is it results in these locations instead. And so here we go from something that had kilometer scale resolution at best to one that now has relative lateral uncertainty on the order of about 40 meters and relative depth uncertainty on the order of about 90 meters. So we can take this now as basically our final catalog, and I'd like to walk you through this and essentially use this to first get a sense of what the fault structure is like in this area, what the geometry of it is, and other features that are particularly interesting. So, so this is, again, this is a map of earthquake epicenters. They're colored by depth. So that means that the shallowest are about 5 and the deepest come close to 9. And we can see here that it cycles in color from white to dark. And so that tells us that this fault surface is dipping to the northeast. And we can look at this in cross section like this. So here we have x prime, and that is this cross section right here. And we can see that all of this stuff here collapses to a very simple surface, at least within this cross section, that is quite localized. It's, at least as viewed from the seismicity, it's on the order of tens of meters wide. And so that is comparable to the relative location uncertainty that we have here. And so it's really not even clear that this is anything wider than, you know, a single surface. And we can look a little bit further to the north, this y prime here. So in comparison, this one is fairly steeply dipping. This one has a lot more curvature to it that shows up at quite small length scale. So it's more vertical at shallower depths, but then it starts to curve backwards. And then it essentially folds back in on itself. So there's kind of a reversal. There's multiple reversals of the dip direction as a function of depth. And that's kind of interesting. One of the things you'll also notice is that there are all of these kinds of high density channels of seismicity that go from high density to low density, high density to low density, and so forth. There's kind of gaps that you can see here, and it's also showing up here, these different gaps. And that actually turns out to be a fairly prominent characteristic of this sequence, and it shows up laterally throughout much of this area here. You can see these kinds of bands of high density of events showing up here, and that's exactly these channel structures that you're seeing right here. We can take this a step further and aggregate all of the events for this entire area and look at the depth distribution. And these high density channels manifest in the form of these peaks here. So you see a peak and then kind of a little trough and then another peak and another trough. And so this leads to these kinds of channeling like effects all within this surface here. So again, this is, you know, the fault normal component is quite narrow, only tens of meters wide, but there's very prominent characteristics along strike when we look at it. And these are all very well resolved by the data. I'll also point out that these focal mechanisms are for some of the largest events. So here is the 4.4, the largest of the sequence, and then some other magnitude 3s. And they're pretty much scattered kind of throughout this area here accordingly. So yeah, so this just also the final thing here, the scale of this is, you know, you're talking about something that's like 3 to 4 kilometers, at least horizontally in dimension. Okay, so hopefully that gives you a sense of what the fault geometry is like for this sequence. We can now move to looking at the evolution of it in time. And so here I have colored each of these events by the time elapsed since the sequence onset. And so 0 is red and blue is 4 years later. And so we can see that the origin of this sequence is right here exactly. And we can see that, again, this clear color cycling from red to orange to yellow, green, and so forth. It pushes up against here and it stops. And so you can see this from a different perspective when you look at this cross section going from here to here, so Z prime. And again, the origin of this sequence is right here, kind of at the base of the seismogenic zone, 8 kilometers. And it's very clear that there is some kind of diffusion-like pattern away from this point here. And it is extremely slow. So this grows from a zone that's on the order of, you know, 100 meters wide to something 30 times larger over several years' time. And that's all within our resolution here. And so interestingly, so it moves up to the north and then stops. But you can see that depth-wise, it continues to migrate upward. And if you look carefully, it moves up here. You can see the color, there's kind of like a light blue color, but then immediately on the other side of this black line, it basically switches to a dark blue, and there's really almost nothing in between here. And it turns out that that is over 1 year time in between this light blue and this dark blue here. So there's basically no movement upward within that time period. And so when you look at all of these features that we see here together, this expansion of the seismicity away from this origin point that I've labeled here, what we believe this to be is that this is basically some kind of natural fluid injection process, some kind of transient process that has started, and somehow you're injecting fluid from below into the fault zone through this point here, and it is diffusing within that fault zone surface through this whole thing over time. And as I mentioned before, it's not moving outward in a fault normal sense because the width of this fault zone seems to be on the order of tens of meters wide, at least as viewed from the seismicity. So it's entirely within this surface that this thing is expanding through and diffusing, and these characteristics seem to be consistent with a fluid diffusion process. We think we can rule out a seismic slip because, number one, the seismicity is filling the entire surface here, in particular once you account for the dimensions of the earthquakes in terms of the slip area. So if this was a seismic slip, it would be kind of hard to imagine how you could go from creeping to immediately seismic to immediately back to creeping again all over the place. It would be very chaotic. And so on top of that, the expansion rates here, 5 meters per day are very, very slow, and they're orders of magnitude slower than anything seen for kind of transient creep events. So we believe that together, all the lines of evidence suggest that this is some kind of natural fluid injection process in the earth. So I want to go back to this here, where I talked about how there seems to be some kind of barrier here. You can see this more clearly because if you look at these events here, so this is a slightly different perspective of that, the events seem to stop right at this barrier, but to the south, they're able to actually circumvent this and move to shallower depths up here. But then later, they basically move along the barrier on the upward side of it with time, but they don't cross this barrier. So it has to circumvent this to the south and then move basically unilaterally to the northwest. And so that seems to be some kind of interesting permeability barrier within this system. I also want to point out that within the fault surface, there seems to be these high density channels again, that I pointed out before when we were talking about the geometry, but here you can see them very prominently. So here's one band here, here's another one, and then there's kind of a pocket of no seismicity at all. You can see another one of these channel-like structures right here, and then it goes to basically no seismicity, and another channel-like structure right here. And again, these are all within the same fault zone. And so there's all these channel structures here, which are quite prominent. And so we can try to understand what is going on here. These observations seem to be somewhat related to some simulations, for example, in hydrogeological capacity. So here, this is just a simulation where if you put a bunch of faults within a medium and the faults have a different permeability from the surrounding rock, this automatically leads to channeling of flow. So here, low or white colors is supposed to be low flow and dark colors is supposed to be high flow, all within this fault zone, just from adding in a bunch of fractures and assigning them kind of relevant permeability values and so forth. And so maybe that might be related to what we're seeing here, where you're channeling flow within this fault zone surface. So we can take this a step further. We can try to quantify the evolution of this process and what we might be able to learn about the permeability of the fault zone from it. And so here I'm plotting distance versus time from this inferred injection point. And again, we can see here that this entire sequence starts basically right here, and it stays very compact for about a year or so, and then starts to expand away from this point through this front with distance away from that point. Now, I'll mention here that these points, so each one of these is an event, and these distance values are not true radial distance. They're actually projected into a long strike and a long dip components here. And so what you'll see is that starting around 2 years in, around the time when this front starts to move through these channel-like structures, the long strike component starts to move faster, which if this is really fluid behavior, then that might suggest that this has some kind of permeability anisotropy that's aligned with those structures within this fault surface. Another thing I want to mention is that starting right at the time of this magnitude 4.4, there seems to be a very clear change in the spatiotemporal character of the sequence. We can see all of this vertical striping here, starting right at this time and continuing for quite a long time after that. But we don't see really any of that before the largest event occurs. And what this really is I think this is just simply a manifestation of earthquake clustering, because you now have this big event here, you put a big stress kick on the system, and you start triggering other earthquakes because you have earthquake stress transfer involved. Whereas before this event happened, there really weren't any large events here, and you're primarily driving the sequence by this fluid diffusion process. And so I think this really provides a good explanation for the effects of earthquake stress transfer versus just a pure fluid source, what that has on a sequence like this. I'll also note that you'll see there's kind of a gap of aftershocks here near the origin that starts to show up, but then comes back once this 4.4 happens. And that might tell us that if this is fluid injection, that the injection source stopped starting around maybe 800 or so days into this process. And the fluid continues to diffuse away because it's already doing that. But near the origin, it stops triggering events until this big event happens, and then maybe it reopens that seal. So, so there's a lot of information here we can get out of this sequence just by looking at the spatial temporal patterns. We can take this and try to estimate something about the permeability structure of this fault zone. If you assume a simple point process diffusion model for pore pressure, you can use these types of square root of T curves to try to bound the front by which this thing expands. And the first thing I'll note is that this doesn't look anything like a square root of T. And I think this is very clearly much more complicated than that. In fact, it even looks like within this expansion profile that there may be multiple kind of sub processes involved or things like this. Maybe implies that there's lots of heterogeneity in the permeability structure and things like that. But what it can do is still allow us to attempt to get some kind of constraint on, the permeability. What are we talking about here? And if you basically treat these as crystalline rocks with a low porosity, we can use this type of bound to estimate something like 10 to the minus 18 meters squared in terms of the permeability of this fault zone. And of course, since this seems to be moving only within the fault zone and not diffusing into the surrounding medium, that probably tells us that the host rock is even lower than that. And so while this is not really, the best model to describe this process, it might still be somewhat useful for understanding kind of how low permeability we're really talking about. Okay, so this is all about the spatial temporal evolution and what properties of the fault zone might control that. We can also take a look at earthquake source properties. And so here, what I'm going to focus on is the earthquake stress drop. So just simply how much the average stress changes before and after the event. And we're going to be measuring this from earthquake body wave spectra. We're using a technique that was developed, over many years by this group at Scripps. And the most recent incarnation of this is this 2017 version from Trugman and Shearer. This is a long established technique where it's basically kind of exploiting the fact that many earthquakes are recorded by many stations and doing essentially an iteratively reweighted least squares inversion for source spectra and path spectra and things like that. So it kind of separates out all of the different propagation and site components. And you end up with spectra like these that we can use to fit source models to estimate the stress drop during each event. And so, so we can do this for as many events in the sequence that we have, or that meet the criteria for doing so. And first, I want to walk you through what happens when we just consider the median stress drop over time. And so here, the median is taken in a sliding window that's 500 events long. And so that first point happens right here. And so this red curve is the median then as you move it along one event at a time. And you can see that starting from here, so this fluctuates around, and the second or very close to the time of this magnitude 4.4, you're going from basically an average stress drop or a median stress drop on the order of maybe 8 megapascals to something that goes to about 2 megapascals. And this is in the median over 500 events. So it's a substantial drop all of a sudden. It stays low like this for several months. And then we observe this recovery, and it recovers to values that are fairly close to what we were seeing before, although it does seem a bit more stable, which is kind of interesting. And so we can try to make better sense of this by decomposing what's happening into events before this 4.4 and after. And so I'm showing you here these events now in a map view form. So these are colored by the log 10 of the stress drop. So there's a fairly large range here. So from tens of megapascals down to much less than 1 megapascal. And you'll see here that, so this is all events before this 4.4 happened. Again, here's this barrier, and where it starts to move up into shallower depths and circumvent this barrier here. So most of the stress drops before this 4.4, everything below this barrier is basically blue and green. So it's fairly high, 10 to maybe 30 megapascals. But as it starts to move up into here, you can see it starts to get red and yellow. And so it's actually dropping quite a bit in this little tiny area here, which you probably would just consider to be noise. However, we now look at all the events just after this 4.4. We can see almost everything above this barrier here is all considerably lower. So it's pretty much all dark red and yellow and so forth. So there's a substantial change in the stress drop above this barrier here. But meanwhile, the events that happen below this are all still generally the same color that they were before this 4.4. So there's clear spatial segmentation of these stress drop values starting around 6 kilometers depth. And because it coincides with this clear barrier to the migration of the seismicity that we interpret as some kind of change in the permeability structure, it may be that this is actually just some kind of lithological transition here that's having a fundamental impact on the earthquake source properties at the same time. So, so if we take everything that we've seen here, we've tried to assemble this cartoon where you basically have this fault zone. It's fairly small, at least in terms of depth. It extends maybe 3 to 4 kilometers depth-wise, 5 to 9 kilometers or so. The width of this seems to be on the order of tens of meters wide. And within this fault zone, there seems to be these channels of high seismicity density alternating with areas of low seismicity density. The migration of this sequence originates from a single point that's on the order of tens to 100 meters wide that we believe is connected to a deeper reservoir that was initially sealed off from this fault zone. And somehow that seal breaks. At that point in time, you start injecting overpressured fluids from this reservoir into the fault zone. And these fluids start to diffuse through this fault zone, predominantly through these channels. And as they're doing so, they're driving earthquakes. And so here, I think, the key really is that you need to really understand the entire 3D structural and permeability architecture in order to understand in order to just figure out why the sequence is evolving in the way that it is. And so this type of process, there's actually a model for this that describes this quite well. It's been around a long time. It's called the fault valving model, and it dates back to the early 1980s from Simpson, and has been worked on by others, Cox and so forth. And this model is exactly this. It's that you have a deeper reservoir on the Earth, and that is connected to a fault zone. And somehow that seal breaks. In Simpson's model, this seal would break because there was an earthquake, a large earthquake, probably at shallower depths, that would rupture down and cut this seal, allowing for overpressured fluids to be injected back through this along a hydraulic gradient and allow for all this stuff to happen. And this would all happen, transiently until you equilibrate and seal back up. So I think our observations here they provide fairly good constraints on this as a viable process for earthquake swarms, or for driving earthquake swarms. We haven't really fit any kind of physical model to the data in order to see this. It just shows up right in the locations when we color them based on the time that they occur at. So I think the interpretation is reasonably narrow here. And we believe that this is fluids again and not a seismic slip, because the seismicity is basically filling up the entire fault zone surface and not leaving a bunch of large patches that, where you could have creeping behavior. And so the last thing here is kind of just a bit of a teaser, and it basically is that this is not unique to this area. It turns out that we've identified on the order of about 100 other sequences just like this over the last 12 years now that have lasted at least 6 months or more in duration. They're all colored here. The sequence I've spent this lecture talking to you about is right here, this yellow one. And all these other ones in nearby areas are also exhibiting similar types of behavior. And so I think together, what we're learning here is that this actually seems to be a quite important mechanism for transporting fluids through the crust in a very episodic manner. So to conclude, we have imaged this active fault zone in Southern California hosting a 4-year-long swarm. We've been able to see important details about the geometry of the fault zone. It's steeply dipping in some places and it has quite substantial warping of the curvature along strike on short length scales. The fault zone seems to have prominent channeling that's mainly along strike, but sometimes along dip. And that channeling manifests in the form of high density or alternating high density and low density kind of bands that are coherent spatially along strike. The source for this process, we believe, is some kind of natural fluid injection process from a deeper reservoir into this fault zone. And this process was sustained, we think, for at least 3 years long, which is pretty remarkable. We can try to estimate the permeability, although there's a lot of assumptions that go into this, and it's clear that a lot of the assumptions are probably being violated. But nonetheless, the numbers that we're getting here are something on the order of 10 to the minus 17, 10 to the minus 18 meters squared. We do see evidence for some kind of permeability anisotropy. It's not super strong, but it does seem to be robust, and it is aligned with these high density channels. And we also see a lot of permeability barriers within the fault zone. Laterally, we don't see that the seismicity extends deeper into the fault zone at any given time during the 4-year period. And we also see that prominent barrier at 6 kilometers depth that coincides with a clear change in the stress drop value. This permeability barrier, this fluid seems to not be able to breach this, so it has to circumvent it, going out of its way to then move within this shallower section of the fault zone. And again, this barrier segments different stress drop values that are quite different. And I think the lines of evidence here seem to point to a structural control on the differences as opposed to some kind of time-dependent behavior. And so thanks for listening. I'm happy to take any questions that you have.